Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over the relationship between the Kp and Kc. Basically the equilibrium constant in terms of pressure versus the equilibrium constant in terms of concentration. So let's get into this. So the first thing we want to do is define concentration, write our expression for concentration. So what is that? So we're going to focus on A, but we can do the same things for B, C, and D. So whatever I'm doing for A right now, the same thing's done for B and C and D. Okay, so if we're focused on A, we can think, okay, what's the concentration of A? So the concentration of A would be, right, in terms of number of moles of a substance over volume. So given a certain volume. So how much stuff do you have in a given volume? That's what we kind of mean by concentration. So if we understand that, we can write that in terms of number of moles, which is going to be the small n. So the number of moles of A in a given volume. Okay, so that's what we begin with. Now we go from there, and now let's remind ourselves about the ideal gas law, because we're dealing with gases in here. So the ideal gas law comes to mind. So if we remind ourselves that the ideal gas law is the pressure times the volume is equal to the number of moles multiplied by the ideal gas law constant multiplied by temperature. Okay, so here we have the ideal gas law, but here we're focused on A, so we want to know the partial pressure of A versus the moles of A. So here we're going to put a subscript A here and a subscript A there. So now we have our ideal gas law in terms of partial pressures and moles of A. And again, we could do the same thing for B, C, and D. So what we're doing for A right now is exactly the same for the others, B, C, and D. All right, so now that we have this, we can solve for pressure. So the pressure of A, if we divide both sides by V, the pressure of A is now going to be equal to the moles of A divided by the volume, and then that's multiplied by RT. So all we've done is that we've divided both sides by V, and we get PA is equal to the number of moles of A divided by the volume multiplied by RT. So now that we have this expression, we can see that we have number of moles of A over V, number of moles of A over V. So now we can substitute concentration of A for this. Since this is the concentration, this is what we mean by concentration. So we're going to substitute this for this. So here, then we're going to write PA is equal to, instead of this, we're going to put concentration of A. So the concentration of A multiplied by RT. And so now that we have this, we can solve this expression for the concentration of A. So we can put this, we want to know what the concentration of A in terms of pressure is. So we rearrange this, divide both sides by RT, and then we end up getting is the concentration of A is equal to PA, the partial pressure of A, divided by RT, the ideal gas law constant divided by temperature. So now we have this expression here. So this is going to come in a little later. So let's now go to our Kc expression. Let's write our Kc expression like we've normally done using our generic equation. So here we have Kc. So the equilibrium constant in terms of concentration is going to be equal to the concentrations of C and D raised to their respective coefficients. So it's going to be the concentration of C raised to the C power, and then the concentration of D multiplied by the concentration of D raised to the D power. And then we have our reactants on the bottom. So the concentrations of A and B raised to their respective coefficients. So A, the concentration of A raised to the A power, and then the concentration of B raised to the little b, oh, oops, it should be a B, not a D, raised to the little d power. And so now we have this expression here in terms of concentration. We have our concentration of A equal to the partial pressure of A over RT. Now remember what I said before, what we did for A is the same we did for B. So we could have the concentration of B is equal to the partial pressure of B over RT. The concentration of C is equal to the partial pressure of C over RT. And the concentration of D is equal to the partial pressure of D over RT. So using those expressions, we can now substitute those in for the concentrations. So let's see what that looks like. So here we have Kp is equal to, and I'll give myself some room. So instead of concentration, so we have concentration of C raised to the C power. We're just going to put in this expression. So it's going to be the partial pressure of C over RT raised to the C power multiplied by, instead of concentration of D, it's going to be the partial pressure of D over RT raised to the D power. And then on the bottom, instead of concentration of A, we're going to use partial pressure of A over RT. So the partial pressure of A over RT multiplied by the concentration, instead of concentration of B, it's going to be the partial pressure of B over RT. And both of these are raised to their power, so little a and little b. So this is little a and little b. So now we have our equilibrium expression in terms of pressure. So now this is Kp. Okay, so we want to get a relationship between Kp and Kc. So what do we do here? So you'll notice that we have some things in common. We have RT. So if we could pull 1 over RT out and then leave the rest, we can kind of see things going on. So let's go ahead and do that. So we have Kp is equal to, and we're going to just pull out the 1 over RT and leave the rest. So here, or another way you could think about it is pulling out the P's and D's, or the PA's and PB's. So we'll take PC. So let's do this. So we're going to have PC multiplied by PD. And then on the bottom, we'll have PA multiplied by PB, the partial pressure of B. So we got those. And then what you can see here, and then of course we have C, and we have D here, and we have the A and the B, so those are still there. And then we just pulled out 1 over RT. So then here we have, and we'll do this multiplied by, and we'll pull out 1 over RT. So here we have 1 over RT, so we have 1 over RT, and that's raised to C, multiplied by 1 over RT, and that's multiplied by D. And then on the bottom, we have 1 over RT, and that's multiplied by A. We pulled that out, and we got that multiplied by 1 over RT raised to the B power. Okay, so all we've done so far here is we took 1 over RT in here and pulled it out there. So it's raised to the C power. So we pulled out the 1 over RTD here, and we pulled it out, and now we have it here. So we pulled out the 1 over RT. So now we have this expression here. So if we multiply these together and multiply these together, then it's going to be, what do you do when you multiply the same things together raised to different powers? Then you add the powers together. So if we do this again, right, so then Kp is going to be equal to, again, this is going to be the same, so it's partial pressure of C raised to the C power times partial pressure of D raised to the D power over partial pressure of A raised to the A power times the partial pressure of B raised to the B power, the little b's power. And then all we're going to do is we're going to add these together, and it's going to be, or multiply these together, and the exponents are going to be added together. So then this becomes 1 over RT, and then that's C plus D. Oops, those should be small. So C plus D. And then same thing with this one. We're going to have 1 over RT. And then these are going to add together. So A plus B. And then, since these are the same, right, if this is divided by this, then remember, if this is this exponent here, C plus D, and you have this exponent here, dividing by the same thing, you are going to subtract the exponents. So the exponents on the bottom get subtracted from the exponents on the top. Given that we are dividing by the same thing, we can then subtract the exponents. So if we write this again, we get Kp is equal to, and again, this is the same. So we got the partial pressure of C to the C power multiplied by partial pressure of B to the little b power over the partial pressure of A to the little a power times the partial pressure of B to the little b. Oops, that should be a D. This should be a D. So partial pressure of D to the D power, partial pressure of B to the little b power. And I keep making this mistake. Okay, so here. So that expression again, and then this would be multiplied by 1 over RT, and then this C plus D, and then we're subtracting A plus B, subtracting A plus B. So here is our expression now. So Kp is equal to this multiplied by this. And so we can rearrange this sorry about that, lights again. So what we can do now is we can rearrange this as follows. Give myself some room here. So we're going to bring this up here. So here we're going to have RT, and we have the partial pressures here. Okay, so actually this should be C here. I made a mistake. So this actually should be C. So right there. So now what we can do is, if you recognize this, this here is the expression of the equilibrium constant in terms of pressure. So that's going to be Kp. So then if we write it up here, so Kc, that's why I made a mistake here. So this should be Kc. So then this is the equilibrium expression in terms of Kp. So then we have Kp there, and then this becomes multiplied by 1 over RT, and then we have this expression here. So that's going to be C plus D minus A plus B. So here's our expression now, and then you can see that we are relating Kc to Kp, and then we can rearrange this to make it easier. So then we could solve this for Kp. So Kp, if we divide both sides by this or multiply both sides by RT, then we get Kp is equal to Kc multiplied by RT, and then we got raised to this power. So C plus D minus A plus B. And then what we could do is, like, this will be this, if we understand what these coefficients mean. So these are the coefficients of the products, and these are the coefficients of the reactants, and these are in the gaseous phase. So these are the difference in the moles of the gaseous reactants and products. So we can say that delta N, so the change in the number of moles of your gaseous reactants and products, that difference is this here. So this is the number of moles, right? So here we have the coefficients. These coefficients represent the moles of your reactants. These coefficients represent the moles of products. And if they're all gases, then the moles of your products minus the moles of your reactants is the difference in the moles on both sides. So we can represent it as delta N is equal to this. So that's going to be equal to C plus D minus A plus B. So we can substitute delta N for that. And so what we end up with is Kp is equal to Kc multiplied by RT, and then that's going to be delta N. And so here, ladies and gentlemen, we have our expression of the relationship between the equilibrium constant in terms of pressure and the equilibrium constant in terms of concentration, our Kp and our Kc. I hope this is helpful. If you enjoyed this video, if you learned something from this video, if you like this video, please hit that like button. Make sure you subscribe to my channel. Hit that notification bell so you can be notified by other videos that I put out. Put a comment in the comment section. Let me know what you think. If you have any questions, please ask. Thanks for joining me, and have a great day.